People want to go somewhere. Hey, Coffee Compiler Club, short meeting today for Too Much Holiday. You're being recorded live. Everyone knows the spiel, that's it. Anyone have something they want to start with? I have a short AA update, which is mostly, I had tons of family and I did a lot of holiday things around Christmas. And I've been porting the last round of theory from a couple weeks ago to the main code base, which is going. It's slow, it's grindy, but it's going. So progress, but slow.
Yeah, I got maybe a practical question. I don't know if the usual LLVM suspects are here. But so I'm working on changing my interpreter to a compiler using LLVM, and actually making quite a bit of progress in the last couple of weeks after the whole moving settled in. But so LLVM does have the option to generate object files. It's kind of two questions. Like, one is the sort of LLVM standard or best practice that you generate one object file per LLVM module, or do you somehow combine them? And then if they are separate, what will be the best practice for linking all that together? Because you can obviously just use Clang or GCC or whatever. But ideally, I would just use like the system linker directly.
You asking me what best practices are?
Just in general, like I know usually we have some people that work on LLVM. I'm not sure if they're here.
Just one comment on the linker.
Ooh, Matt.
If you can avoid using the data system linker.
Matt, your sound quality is very loud. And
Testing 1, 2, 3. Testing 1, 2, 3. Is this better or is this worse?
It's a tiny bit better. It's like you're talking in a tin can.
It must be the microphone.
Move it further away from your face.
Yeah, just a moment. Hello now. If the
volume's better.
Now it sounds like you're underwater.
Yeah.
Fantastic. I need a secure location. Anyway, then I think that if you can, try to avoid the system linker if that's because the performance of that is not good.
I cannot make out what you're saying.
Okay, I'm going to switch to another.
It's something with the noise canceling. Like I think that's what it sounds like. Is that it's like you're having a feedback from the microphone, and then the noise canceling is cutting out your voice.
Oh, usually you have to dial it down, so the echo will disappear.
Yeah. Oh, I don't know.
All right, we'll give you a second to sort your. Yeah, there it is. Try more hardware. Right
I guess in the meantime, I could just do an update on.
Yeah, do an update.
Progress.
Yeah.
I mean, progress as in I still have like 150 to-dos to go through.
Welcome to the club.
Yeah. Most of those are just port this instruction to machine code. But I like outside of moving houses, I was sort of going through them like instruction by instruction. But I kind of realized that it's a little demotivating because I have to port like 200 something instructions and you don't know if they work until basically all of them are done. So I took a small detour where I'm now trying to sort of work my way towards being able to print hello world again.
Yeah, right.
And just only implement what I need for that. And then I can sort of incrementally test that. And then along the way, been not so much reconsidering, but reinvestigating how I compile generics. Because right now I don't. it's basically boxed
So
type erasure.
what's the plan? What's the plan?
So I have this I think somewhat sort of unique situation where I use a combination of single ownership, but with runtime semantics, that being reference counting. And so at runtime, and to make it more complex, most values will use normal reference counting, but a couple of them will use atomic reference counting. And that's so that those values can be shared between threads more easily. So I have this problem with generic code that you need to know, okay, is this an owned value? If so, we need to discard it, run its destructor, etc.
So
but if it's a reference, we just have to reduce a reference count.
Mhm.
So the way I do that now is by pointer tagging, which is mostly a
Mhm.
artifact from when I'm using a
You
interpreter.
have to propagate that information from time. So
Yes. So what I have now for heap objects, I set a certain pointer bits to indicate, hey, this is a reference. This uses atomic reference counting, etc. And then for integers, I use the lowest bit. So 63-bit integers don't need heap allocations. 64-bit integers, they are boxed as a fallback mostly. And this, conceptually works, but it means that every time, for example, you have a generic function where you create a reference to some generic type, you start with this branch like, okay, is it a reference? Is it this? Is it that? And you do that every single time you create that reference or drop it. So it's not ideal. So I've been looking like the usual suspects, monomorphization. I'm just going to refer to as specialization because it's much easier to roll off the tongue.
the same thing, yeah.
I looked into the Swift approach where you essentially pass hidden arguments describing the types.
Mm-hmm.
The boxing, which I think what OCaml does. And as far as I basically concluded, the only way I can get rid of these branches is if I, at the very least, specialize by ownership. Or I guess specialize by reference kind, as I think about it. Term.
Yeah.
Because all the other approaches, you have branching at runtime, and you cannot have both unboxed integers and floats. You can have with tagging, so you can have 63-bit integers, but that means every time you use an integer, you have to untag it, do your thing, tag it back, etc. But right now, I'm basically trying to sort of keep my current system because I know all the LLVM work is already a lot of work, and also having to redo generics is quite a challenge. But it's I already got sort of sidetracked for a couple of days going into this, and I was like, no, let's do the LLVM part first because otherwise it's going to take another 6 months. I did find a paper where I think, let me see if I can quickly dig it up. I will dump it in the doc. It's a paper called Kinds Are Calling Conventions. I didn't read it fully. I just sort of skimmed through it. From what I understand, it sort of discusses this very idea, like instead of specializing by type, you sort of specialize by, I guess, shape or reference kind. Basically, if you have like 15 different types that translate to word-sized pointers, you don't generate 15 different copies, you just do one. And I think that something like that might provide a nice balance between the benefits you get from specialization versus the compile time performance. Because the whole
something is wrong with the link. Give me some minute.
Let me see.
Which link?
The posted link in the docs for the paper.
There's a G at the end. There you go.
That's fine.
Yeah, because the reason I didn't specialize before is because I really didn't want to eat the compile time cost. All that, and everything was boxed anyway, so it didn't matter.
Wow. Yeah, watched the Julia folks try to do incremental jitting with LLVM with a bajillion specializations by default. And they died the death of a million LLVM compiles. Startup time was like 10 minutes to get past, hello main, whatever main, because statically declared types had to be jitted. And so you couldn't hit main without like 10 minutes. So people went through giant hoops to avoid restarting their instance once it got up and in the debugger because it was such a nightmare to restart.
Yeah, and that's my main concern with using LLVM, that like every other language using LLVM, people are going to complain about the compile times. But the thing is there, I looked at two alternatives, which is compile to C and use this Rust library called cranelift. Compile to C, I think it's it depends on what compiler you use, whether that actually helps. Because if you use Clang, you're still using LLVM, so it'll take time.
Aren't there like faster C compilers out there though? I mean,
And you have
certainly
GCC on Linux, and then you have Tiny C.
Yeah,
from
okay.
Fabrice Bellard, but last I checked, it does support C99, I think, but everything
You're
after
generating it, so you just generate the subset they take.
right. But point being, Tiny C isn't actively maintained, and
Oh, fine. I mean,
I think
there were small C compilers when I was a young guy that were super fast on purpose. That was their schmick.
right. And so this is that. I think the other thing. There are a couple of reasons that put me off. One is you're dealing with C, and I don't trust myself to generate C that is not relying on undefined behavior. Or it is in some way problematic.
Yeah, but only undefined for the one compiler you're targeting too.
Right. But then the second, there were these differences in the compilers that were annoying enough. So, for example, Clang and GCC, they all have built-in functions for doing things like checked signed integer arithmetic, which is kind of important for my language because integers overflow. This language panics upon integer overflow, and I use signed integers. And conveniently in the C spec, this is all undefined behavior. And you can do things like, if the compiler uses 2's complement integers, it's probably fine, but then you need a check for that. So that's kind of where the differences pop up, because GCC and Clang have functions for this, but Tiny C does not.
One system on the planet that's not using signed 2's complement arithmetic. If you're not compiling to like Honeywell machines being used by the FAA for controlling planes, then you're not using anything but 2's complement.
Right, and so there are checks where I piece together some macros that will error out if you're not using 2's complement and stuff like that. But it's more that because it's undefined, even if the compiler uses 2's complement, they can technically optimize it away. So it's kind of like, it probably works fine, but we can't guarantee it. So I didn't want to deal with that.
Okay, fine. Let's say a lot of stuff that's undefined in the language that there is a strong expectation you will behave this way. And if the compiler doesn't behave that way, there'd be so much screaming.
Right. Then the other is cranelift. It's a code generation library in Rust. It primarily targets JITs, so it's very fast, that sort of thing. But the documentation is basically non-existing. Mm-hmm. It's like a simple example in their VP where they don't explain why they do things the way they do it. Mm-hmm. And beyond that, you basically have some projects that are like 4 years old and use an API that's no longer available. And there's a whole bunch of stuff just not implemented yet. Again, checked arithmetic is not implemented, so you have to.
It's got to be a better jitting setup than LLVM. Just amazingly bad.
Can you hear me better now?
Yes.
Oh yeah, much better.
Okay, I have changed the hardware. So one comment for Julia, actually using object classes helped a lot. They speed up the startup time from something like 2 seconds to 1/4 of a second for some benchmark. So that's a recent addition, so this may be worth doing.
Yeah, okay.
And the other comment is, you mentioned system linker, and depending on the system, I would advise against that, because if the system linker is GNU, it's going to be horrible. It has very, very bad performance. If you're using LLVM already, it ships with LLD, and that's going to be much better. As in the difference for Chrome, linking Chrome takes 40 seconds on a 128 thread machine. So it's going to be much worse than that, of course, on an ordinary laptop, and that's with GNU BFD. But with LLD, it takes something like 4 seconds, and with Multi, it takes like 2 seconds. So it's a pretty sizable speed up, or a slowdown if you use the system linker.
Right, I think it should have probably been a bit more clear there. When I mean the system link, I didn't necessarily mean your LD dot whatever. It's more like you have an executable that happens to be the best linker for that platform. So on Windows, that would be not cl.exe, but the other one.
Right.
Link.exe from Microsoft, but you can use LLD from LLVM for anything. So it's going to be Windows, Mac OS, Linux. I would just go with LLD if you're always using LLVM. It's not going to be additional dependency for you.
Well, so that's the thing. My compiler would use LLVM, but once that compiler is built, you should be able to run on a system that doesn't have LLVM installed. Although I probably have to statically link LLVM, but point being, it's kind of similar to, for example, Rust, where they use LLVM for a compiler, but they support swapping out the linker that you use. I think they default to just CC on Linux, but there are flags where you can say, hey, use LOD or use mold or whatever. The reason I asked is because from playing around a bit, if you use Clang, for example, and it's very straightforward. You list your object files, your libraries, off you go. But then with LLD, for example, it needs extra arguments for like system libraries and things like that. Basically, Clang does some extra sort of magic to resolve, I guess, extra dependency for you.
Yeah, it is in the driver. So normally, at least for C and C++, you wouldn't even manually invoke LLD, but you would expect the Clang driver to do the job for you, in particular the system libraries that you mentioned.
Right. Yeah, I suppose probably as a starting point, I could just sort of thread it through the system compilers on Windows. There will be cl.exe, I guess. Then Mac and Linux, you just use, CC, for example. It's just more because LLVM has all this stuff. It's kind of okay. Maybe they have some sort of library where you can do this instead of having to like shell out, but haven't been able to find anything.
Right, I would look into what the driver does. I'm pretty sure Clang has to have some logic for this, but I haven't looked into this myself either.
So, getting back to cranelift, so I pasted a link into the docs. So I don't know if you found this, but like there's this page that says cranelift documentation, and it has there's 3 pages that kind of give an overview of cranelift, and then it has links to all the Rust documentation. So it's sort of like Java doc, but for Rust. So I was wondering if you found that, or if that was part of what you didn't consider good enough, or whether it was.
Right. So I did see that. I went through basically all of it. To me, there's sort of 2 parts documentation. You have your API docs and you have your sort of user guides. LLVM in that sense does a really good job at both. Well, the API docs is kind of incomprehensible for me, but the user guides are great. And the Rust bindings that I use, they have also good documentation. So the main issue there is trying to figure, okay, I have this concept, which functions do I need to use for that? But then once you have that, you can sort of figure out from there. And I notice myself, once I sort of get started, it's much easier to find things based on what you already know. And they have, the whole kaleidoscope tutorial and all sorts of things. Cranelift basically doesn't have that. What they have these sort of high-level overview of the IR, some of the general concepts, things like that. There are some old projects that I found that use cranelift for compiling a language. Most of these were a couple of years old, using older APIs, and basically all of them, they use the JIT API. Specifically, cranelift has this sort of JIT replica there, cranelift simple JIT or something, and they generally use that. But I was more interested in producing actual object files and basically ahead of time compilation. I found one project, I don't remember the name of it, but the recurring issue is basically it's not clear sort of what functions you should use for what things, if they're implemented. So for example, let me see if I can quickly, let's say checked integer arithmetic. So cranelift defaults to wrapping on overflow. But there's no mechanism to detect when that happens using, say, a carry bit. And people might think, oh, overflow for addition is easy to check. Well, if you do, positive plus negative, there goes your check if one is less than the other.
Well, all right. I mean, the reason I'm worried, so my plan is not to use any project. My plan is to write a native x86 backend. But I was sort of thinking, I sort of like the design of cranelift. So, but it sounds
so
it's just not documented enough. to use.
So I really like the idea where they're heading, specifically focusing on fast code generation. And I chatted a bit with them in their Zulip, whatever chat, etc. The sort of summary of it as a whole is, I think that at this point, cranelift is probably in need of another 2 to 3 years of development before I would recommend it for any serious projects.
So the problem with cranelift is where it's getting used successfully is the places where the contributors are actually doing the work, right? So the so yeah, I was going through a similar path just a couple weeks ago, so it's kind of funny that you brought this up. But you know, you can't tell what's implemented or not without actually going in and failing, right? And you know, there's a lot of documentation, but there's no like standard platform, so to speak. So there may be documentation for something, but it's like not included, and then you have to like go and find it and put it in yourself, and then you find out there's a version mismatch, and you've got to, you know, bring it up to snuff yourself. And so it's definitely lacking about, you know, well, it's definitely lacking a manager for the project. But the tech is cool. I you know, it's obviously, you know, it's obviously fun from a someone's having fun working on it. I was looking at it mainly within the context of WebAssembly, actually, which it's used for a number of things in the WebAssembly world. Which, but it's not. I wouldn't call it mature by any stretch, and it can be fairly frustrating because you may stumble on doc and you're like, "Oh, this is exactly what I need," but it's not at all like plugged into the actual project. So you're like, oh, well, I need that library. Now, how do I get it in? And yeah.
Yeah, to give an example of that, again, signed integer, or sorry, checked integer arithmetic, there's no instructions for it in the IR. And there is some parts somewhere where it has sort of preliminary support. I don't remember if it was in the IR of like a layer further, but it's basically at a point where you might be led to believe it supports it, but then you dig down and you find, hey, when they finally get down to the point where they start generating the instructions, that's where it will error out because it's not implemented. And so there's a pull request where they add some of this for x86, for example, but not for ARM, PowerPC, or basically anything else. And that's not clearly indicated. So you go through the docs and you have no clue, okay, is this actually going to work? Or am I going to spend, you know, weeks implementing this? And then I found out, oh, 1, it's not supported. 2, the developer's not really interested. I don't know how to do it, which means 4, it's going to take 6 months. Right?
That's exactly what I found as well. So yeah, so you ended up pretty much in the same spot.
Yeah, and that's why I said I think it needs another 2-3 years. And I think for me, the final concern was that right now, it's basically used for 2 things: for WASM WebAssembly time. I don't know how they intend for you to pronounce it, but WASM time, I guess. A WebAssembly interpreter and JIT, and there's a Rust backend that's using it. And I did look at that, hoping to sort of learn more about it, but it's a full-grown project, so good luck trying to figure out, you know, how it works, why they're doing things. And they ran in simulation, so a lot of the problems I ran into, they sort of solved it by emulating it. So checking for overflow, they emulated like platform-specific bits and pieces. And it's outside of that, it's not really seeing any use, which means that if this WebAssembly company behind it, I think they call it like the Bytecode Alliance. If that one goes under, that means basically all the developers are unpaid, and one of the major use cases is gone, which I strongly suspect basically means the end of the project. Because yes, there are people using it outside of that, but I don't think those people have time to maintain both their project and this whole compiler infrastructure. I certainly don't. And that's why in the end, I ended up going with LLVM, because it's been around for 20 years. It's probably going to be here for another 20 years. It has everything. The only thing it's lacking basically is compile time performance. But as far as I understand, that is becoming more of a priority. people started measuring it in the recent years. So, maybe in a couple of years that's going to be better.
Yeah. I've been watching the compile speed performance of LLVM for 20 years, and it hasn't been going upwards in that entire time. So I'm not holding my breath. Maybe.
No, and I think at the end of the day, the benefit of it, as far as I understand, it's mostly an issue of how much code you feed LLVM and how much you want it to optimize. And so in theory, you can control that by doing more yourself on your own IRs, etc. In theory, I don't know how practical it is and how it works, but it's
we need
of all the problems you can have, it's probably the least problematic one. Whereas, hey, we have this instruction set, but half of it is not implemented on the x86 backends. That's kind of a deal breaker.
Yeah, Arthur's the guy who's been hacking LLVM to feed it profile data and hacking it to hand it IR that he's coming out of Java bytecodes. I assume he'd have a pretty strong understanding of where it's at in terms of compile speed and the like.
One way you can still play the trade-off is to have an interpretation tier. And there is a bunch of database work when they are using LLVM for query compilation for a database engine, and they run into the exact same problem in that the compilation time of LLVM alone would outweigh the benefits you would get in the faster execution time if the query doesn't repeat frequently much. So what they do is they added another point to the trade-off when for the initial queries that do not execute a lot of times, they just interpret the LLVM IR. So they wrote their own interpreter for the LLVM IR bitcode. And only after another tier, once you get this execution frequently enough on a large enough data, will they actually run the JIT compilation on the LLVM IR that corresponds to the query. And they have a very nice feeder in this paper. If you go to the feeder 2, you are going to see this nice trade-off between what is the execution time and what is the compilation time. And you would get exactly the shape that you would expect of this decaying exponential curve. So there is a point where it pays off to have the interpretation tier.
Welcome to every JVM everywhere, except 20 years later.
Yeah, so something I've been wondering is whether it's feasible to take the code generation of like a JIT compiler, like the JVM or like V8 or something, and then use that as a backend.
Well, that's what you use the JVM for your backend. The issue you have there, of course, is that there's such a tight integration between the generated code and supporting runtime that teasing the two apart in a meaningful way is really difficult.
Okay.
So if you took like OpenJDK and said, I'm going to hand it something other than Java bytecodes, I assume you're going to hand it something with new semantics that are not easily expressible as Java bytecodes. Now you got to sort of eat the whole ball of wax at once.
Well, I mean, I'm going to I'm thinking lower end. Like I'm thinking maybe because I'm pretty sure there's a step between the bytecodes and the assembly that's like like the sea of nodes stuff, for example.
Yeah, right. Yeah.
So
yes and no.
If you generate a sea of nodes graph, can you can you generate code from that?
Yeah, that's what I'm trying to say here. There's a tight integration of the runtime. Yes, you can go generate machine code if you fed C2 a pile of sealed nodes. He would also generate OOP maps and want to put them somewhere for a garbage collection and safe points that if you hit this code, you need to jump to some other execution strategy like the interpreter or whatever it's going to be. And you have to describe how you're going to hand off where the compiler gives up in the form of Java bytecodes, because that's how he's going to describe the give up point and go back to whatever you're going to run next. Like you handed an IR that included a semantic that was basically act like Java bytecodes here. And then, the compiler decides, I'm going to give up now and go to the bytecodes instead of actually taking it directly. So gives a bunch of other things that are tied to the runtime. Like he asks questions of the runtime that you would have to be able to answer. How many classes, subclasses, subclasses does this guy have? Walk his subclass tree looking for abstract and missing pieces.
So there's a lot of assumptions basically.
So
Yes,
what
there
I
are.
heard, yeah, the
You have to hack
the
some that you might as well write a new piece of code.
Yeah, I'm not claiming that, but I think it's pretty close to that. Yeah, I like in my head, and I know a hell of a lot of what goes on there. The surface area of the interaction between the compiler and the runtime is large, and it wasn't ever designed to be small, and it got smallish. There was an effort made to bound the surface area more reliably. I claim that showed off just how fucking big that surface area is, and it's more obvious now that there's a compiler interface in the core hotspot that wasn't when I started. It's ugly and it's huge. Could you make it smaller? Sure, especially if you knew up front you're making a portable JIT for other people to write their languages in. Nonetheless, it's never going to be small. And the one in hotspot's big.
Yeah, I mean, there are portable JIT projects that were written for JITs. I forget what they're called, but I mean, there's Google.
PyPy had a couple, made an effort to be more than just Python.
Yeah, but like the Lua JIT thing, I think like, there's like a one file, like macro thing that he says.
Right. I've heard good things about LuaJIT for simplicity. Like maybe it's not the best code, but it beats your interpreter. And if it has a tiny interface, you might like that as a alternative already. We talked about LuaJIT sometime in the past. Gosh, I got too many open windows.
Of course, one easy design point is to disable optimizations in LLVM, and that may already give you some speed. In this database paper, for example, they analyzed the contribution of each part of the LLVM JIT compilation pipeline, and the middle-end LLVM optimization passes actually counted for something like more than 50% of the entire compilation. So if you just disable some of the passes, I would just keep the MM to reagent and scalar replacement of aggregates, for example, because you don't want to build the SSA form yourself. And those two passes will actually take the LLVM IR with memory, load and store operations, and they will create the SSA with the nodes for you. So I would just try with a very minimal set of passes, and you can always add more and see if the trade-off works for you.
That's the C2 sea of nodes versus LLVM policy theory, whatever. Straight to SSA from the get-go, never come out, and there's only one major optimization. You don't want to drop it anyhow. It's faster to run it than to not run it. Fine.
Oh, so you create the SSA fee node directly. You never optimize anything away.
That's correct.
That's kind of nice. Okay.
They're generated out of the parser. They're optimized like anything else optimizes. They frequently optimize away immediately after being constructed, and the memory is just recycled, reused for the next node. Like the generator for SSA does the obvious thing that I've talked about here, like easy SSA talk I gave. The prompt next answer is, if you don't use a value in a loop, like the fees only show up for free, like uselessly at a loop back edge, at the head of a loop, because you don't know what comes on the back edge. Immediately when you close the loop and the back edge closes, if you never use that value in the loop, the fee goes away at that point. Before you're done parsing even, it just, you fold it immediately.
Yeah, so I would expect this to be faster, and I would expect you actually getting pretty good performance even without that many optimization of this. This actually used to be the strategy for the C and C++ compilers. Before GCC adopted SSA and before LLVM was even a thing, you would see that the C compiler emitting a code with low optimization levels actually would outperform what you nowadays get with O0 from Clang. And the reason is that Clang with O0 is going to emit load and stores for every single operation, even something like a variable on a stack. You often just load the variable, modify it with an operation, and then store it, and then you immediately reload it, modify it with another operation, store it back, and on and on and on. And that's because of this design when the frontend only emits loads and stores, and it is the responsibility of another pass to create SSA form. But if you do not have this separation, you can actually get pretty good performance for low optimized code. So this is an interesting point. You will face some difficulties, of course, if you're writing this from the scratch and you are not Cliff. You may want to be careful when creating and destructing SSA form because there are some tricky bugs that may appear in that. But it is definitely worth exploring.
I'm claiming SSA is fucking easier than hell to implement, and there ain't nothing clever about it.
Well, there are some bugs like with this parallel copy problem and how you think about the multiple edges, reaching one control block or splitting a critical controller. I mean, it's all engineering and it's all doable. You just have to think about it.
Okay, so I'm going to separate out making SSA form from emitting code out of that SSA form you just made in register allocation. Because what you just said was register allocation problems, which every register allocation has to deal with no matter what.
Oh, no, I just meant the destructing SSA form.
Yeah,
Unless
right.
we are talking about the same.
So you don't destruct SSA form.
Until the backend.
No, you don't destruct SSA form ever. The backend's still in SSA form.
Just
It's
so
different than
which form
LLVM then. Because in LLVM you do come out of
I'm just saying, go into SSA, never come out, ever.
Okay, that's what you do in situ.
Say it again?
That's what you do in situ.
Yes.
Okay, got it.
And then you do some things at the back end that the register allocation has to deal with that look like it's going, well, it's the same problems you have in the register allocator, whether you're in SSA form or not, but you don't have to deal with it. It's not part of SSA form, it's part of the register allocator. The whole cycle of assignment problem, that's a register allocation problem. He has to deal with that. No matter what your IR is.
No, fair enough. I get what you mean.
Yeah.
One issue though is that you still have to take a little bit of effort to preserve this in some of the transformation passes, right? I mean, thinking of things like breaking a critical edge between a basic blocks and then fixing up the destinations and the sources in the fee nodes.
So
I assume you have to maintain that, right?
So when I build the SSA form, the fees go in at every merge point, like you'd expect. If you later decide you want to break a critical edge by cloning code or whatever, there's a very straightforward graph transformation that does that carries the SSA form through correctly without sort of any brains involved. It's a simple people optimization. It just rewrite one set of things into another straight up as a, I don't know how just like I need to show you a graph picture, but it's the obvious graph you would draw when you were doing it yourself, not in SSA form, but the same thing happens in SSA form pretty much in the same way. There's nothing going on there that has anything to do with SSA. You carry your fees through, but that's part of SSA, and that's the only thing that's happening, except you would carry the fees through anyhow.
Fair enough.
We should pull up a graph, like draw some code or write some code that in SSA or not SSA, and then show it before and after the critical edge split. So write it with and without SSA and have a critical edge that you're going to split, and then write it after the split. And I'll show you where the fees go, and then we can talk about the graph transformer you want to do there, but it's going to be a dumb one.
And as far as the front end is concerned, you wouldn't say that in your experience it complicated the front end implementation for you.
No. That's exactly what I'm saying here. I took it from bytecodes to SSA form directly. Well, I'm doing it from AA, which is basically C-like syntax, to SSA form directly. It's straightforward. I'm not building an AST. I'm building SSA form directly. It's
all right, and just start with the bytecode already.
For the Java case, I start with bytecode.
Right. That's a little bit different than the C or C++.
Right.
So maybe that's the source of the difficulty, because for C front end is basically what operates on an abstract syntax tree and emits LLVM IR. And LLVM IR is like the first lower level tree address code style intermediate representation you get in this pipeline. But if you start from the bytecode, then maybe it's actually simple enough.
You could start from an AST and go to SSA form from an AST.
What Cliff is saying is just skips a step because it's easier for him to work in SSA than in AST.
Well, I'm saying that if you go to SSA, you are funneled down this path where there's an obvious big optimization that's cheap and easy, that covers like 90% of the passes you get out of LLVM, and it's super fast. And it gets this whole, I have reasonable code quality and I get it cheap and fast. And people who hack on, you know, C2's IR come around to the same point pretty quickly. Like, oh yeah, I see. It's.
But if C2 and LLVM basically does the same thing in spirit, why the performance difference?
That's because I skip all the steps to get the same thing done. That's what I'm saying.
For the optimizations, I mean.
Yeah, right. I skip all the in and out of SSA, or everything else that happens on the SSA form turns into, it's all incremental. Sparse and incremental, which goes straight to fast.
I got that if you work into the whole graph representation and rewrite it, it's easier to work with it from start to finish.
Yeah, I mean, there's a design philosophy change there. So the original comment that got me down this path was just, you know, LLVM slow and been slow forever, and I get equivalent performance, not identical, but equivalent performance 100 times faster than LLVM.
That was my question. Why is there such a difference? Why there is such a fundamental difference between frameworks that basically does the same optimization?
I preach the SC of nodes, and people take it or they don't. It's not my job to force you. So LLVM started on that path before they saw C2 or understood it or something. And then there's just this large class of people that think and deal with it that way.
That's fine, but it's been 20 years. Why they're being able to pivot to bridge the performance gap?
I don't know, and I'm not. You know, it's not my job to evangelize more than I am. This is well past where I care. Like I said, if people do the pivot, you see it in their eyes. They light up and like, holy shit, this is so much better. What the hell? But the count of people that do the pivot is, you know, measured in the dozen. Fine.
Well, if I could make a guess, you know, I mean, I think you aren't really answering Theodore's question when he's asking why LLVM is slow, but like, I mean, Sea of Nodes, it basically does everything in place. Like you have a node and you just modify it incrementally.
I'm sorry, it does everything in what?
It does in place. Like it doesn't copy nodes around. So like, you know, like it allocates a new node or it modifies some pointers in the node. It doesn't like, it's not always moving things around. Whereas
my hunch is the core optimization is because it's incremental. You don't do the work more than you needed to and incrementally get better. That's one of the hearts I got through the months of.
There are a couple things that go to speed. One of them is exactly incremental. Sparse goes to small memory footprint, which goes to, it's all sitting in your caches instead of foaming in and out of the main memory bandwidth. There's no rewriting the entire IR over and over and over again. I do rewrite it a few times, but in general, it's update in place, as you were pointing out. The rewrite it a few times happens because
but it's not uncommon knowledge to work at the compilers work with different IR with each step. This reasoning goes directly opposed to this. You have a different IR for different stage of transformation.
Right, and I have just the one IR, and everyone understands it, and it is understood by everybody. So things that happen on it are all done by the one set of code, not by separate unique code, which requires a copy.
Just out of curiosity, do you also do instructions scheduling in the backend on the same IR?
Yeah.
Interesting.
So when I come out of the SSA form, I leave it in SSA. When I come out of the Sea of Nodes, is a better way to put it, I go to basic blocks with a list of instructions that happen to have SSA def use edges all throughout them as well. But now it looks like a traditional pile of instructions.
Okay, and the instructions that appear in those basic blocks are no longer one-to-one to what you would have in the Sea of Nodes initially.
Yes.
Okay, so in a sense, that is a different IR too.
Yes, it maps from an ideal IR to a machine-specific IR as one of the stages.
Okay, I would say that's pretty standard. I mean, that's also the case in LLVM. You have different IRs, but it's only because you have to have some tie to the instructions of the machine at the end of the day.
Yes, yes. And those machine instructions they inherit from the node class. They look like nodes in the graph. All the standard node editors work on them, but they also carry shit like, and this has a shift by 3 hard coded in it, and the 3 wasn't necessarily an input to the node; it was buried inside of the node. It's a shift by 3 and add a base, and it's an Intel address.
One architectural challenge in LLVM that I find myself facing sometimes is how to backpropagate this knowledge effectively before you lower to instructions. So what I mean by that, in some of the loop vectorization passes may or may not be beneficial depending on the actual latency and resource usage at a particular microarchitecture you are going to be targeting.
Yeah.
And this is strictly backend knowledge. I mean, you actually have this knowledge in the LLVM backend. You know that machine instruction such and such is going to map to this and this execution port, but you definitely do not have this mapping knowledge at the middle end loop vectorizer stage, because you don't even know what the instruction is going to be like. Have you ever dealt with something like that?
So So C2 does short form vectorization, expecting SIMD instructions to pick it up, but it does not take a lot of backend knowledge into that vectorization. So I said I get nearly LLVM, but I don't get LLVM. In particular, I don't do fancy array loop nesting blocking games because it's Java arrays and not C arrays or Fortran arrays. But this is a case where it's easy to feed that information back to the vectorizing. You just have an API that says, go ask the backend what'll happen here. But,
right, the challenge is that you're still at a different IR, because if you are doing this in the middle end, then you don't yet have a notion of what instructions are going to be emitted for the vectorized version of the code.
But you generally know what instructions you're hoping to get emitted by that point. Like C2 comes along and says, okay, so just be clear. So there are certain codes that I know C2 will emit or not emit according to what the backend is going to spit out here, and he'll deal with that expansion when he gets to the backend, but the middle end understands that this mem block is free or not free, or the cost of a mem fence, because on x86 it might be a no op, and an ARM it'll be really expensive, and he'll do something different. So he'll ask a cost model from the back end of what he expects the implementation of this thing will be. So I'm doing SIMDIs, loads and storage. I'll ask the back end what I expect the cost model will be. If I'm on a piece of hardware that doesn't do SIMD ops, I won't do SIMD optimizations, because I'll go ask the back end from the middle end, hey, if I were to SIMDize this, would it be beneficial? Okay, that's one question. And then another one is, hey, can I use, multiply, add, combined? And, do the bytecodes allow it? That's one question. And the other one is the backend going to do something special with it? The answer will come back yes or no. So there's a bunch of these questions the C2 will ask to help it guide, but it's not doing a giant back and forth game.
Right. I mean, that's also not the case in LLVM, because generally you will not have a very precise knowledge. You will not know which particular FMA x86 instruction you are actually going to use, for example.
That's correct. I assume I'm going to get an FMA, and I can arrange for one, but I don't have a particular, and so
you
I
have
know there.
More of a coarse granularity in the cost model that you have a cost generally for FMA, or maybe FMA for this and this many bits, but not like the specific microarchitecture implementation of a specific FMA instruction.
There is I definitely ask questions that vary by the x86 microarchitecture. But that's sort of like, what's the interface to the back end from the middle, right? When I'm in the vectorizer and I'm like, how many times do I unroll this? And one of the questions is it got too big? Is it possible to unroll? Is it this? Is it that? There's the usual things. Okay, then I come down to, hey, is it going to be super cheap after unrolled and refolded, because there's going to be 128-bit FMAs or whatever the hell's going on? Some of those I can start to ask the backend up to some limit, and then I don't necessarily have a giant pipe API to the backend to say things, and I don't know what instructions will show up directly. But I can mostly guess that if you're doing normal array math, you'll get normal x86 addressing modes. Those are like going to happen pretty much hard guaranteed. And if I arrange the loads and stores to be all politely aligned, and I pass that metadata along and just see if it's easy to do, then I know the backend will throw in 128-bit alignment if it has it. And then will that make a difference in how much unrolling I should do? Maybe, maybe not.
Right.
if I enroll it to too few times that you can't use your 128-bit versus your 64-bit versus too many times, a little bit on the too many side, it won't blow out your iCache and it won't matter.
For x86 Intel implementations, one interesting trade-off is that port 5 basically is what I'm talking about. There is a lot of instructions for x86 Intel that only use port 5. And sometimes it's actually better to go for worse latency, worse throughput, and emit more instructions just because they are going to use, say, port 0 or port 1.
Right.
And that kind of knowledge, in my experience, has been non-trivial to propagate back to the middle and from the back end because you don't have the resource utilization yet at that stage.
So for when it gets down to that level of thing, I usually just let the back end deal. So I did some amount of unrolling and I arranged for it to be conveniently vectorizable in some level. And then I hand it off to the back end. The back end can look and say, here's a pile of instructions in a loop. I'm going to emit code for them or whatever I'm going to do. I'm going to flip it from virtual to machine or idealized to machine instructions. And he'll make a call then if he wants to use versions that have fewer ports or registers or whatever. So there's a handoff and then the back end picks given the instruction layout. And in my experience with this for Java, at least, it's very close to what you're going to get that's sort of idealized, but it's never, you're not perfect, but you're damn.
All right, I'm already talking about squeezing the 1%, the last 1% performance at 99% engineering effort, of course.
Right, generally I get 5% by a major register allocation improvement and 5% out of a major inlining hack, and I don't really care to push hard on 1%ers. Right, so in the many years I was at Sun doing the compiler, after you got the first tier of inlining done, the next big gains you got was a second tier of inlining smarts and a second tier of register allocation and a few things to do with instruction selection and a few things to do with scheduling, but these are all much more diminishing returns than better inlining choices.
Right.
And actually better profiling data, like go back and add profile counts where you missed them in the C1 tier. And then that both gives you better inlining choices, but it gives you better instruction scheduling choices and code layout.
And it's good software engineering in general that you have modularity and you don't mix up your middle-end implementation with the backend. One challenge, I wonder how is it going to work in the future when we have weirder and weirder hardware with weirder and weirder instructions like AMX. At some point, you may want to see that you have a bunch of 8-bit integer multiplications in the middle end, and you would like to know that you're going to have the AMX instruction available in the backend. So that may mess things up a bit.
Well, that gets back to, you can ask some of these questions you can ask from the middle end to the back end. But yeah, I'd leave the middle end as idealized ops. And actually, when I go to the SSA on the machine ops, I do retain the edges. So I have def use edges. So I have dependencies straight up on the normal graph layout. But you lose some other things. I keep the
at some point, I guess you lose the dependencies, but at least at the register allocation, you may have the same register used for what used to be different, right?
So you leave the edges in the graph because that's def use sparsely. So that's like hugely beneficial, even for the register, especially for the register allocator, actually. And then the register allocator inserts nodes to break conflicts. And the nodes are copies. And the copy, for my case, the copy was something that'll move from one register class to another. So maybe in a register class would be memory, so stack spills or not. Or just from AX, BX. So you return from a value from a call in AX, but you're going to pass as an argument to the next call, and that's in CX. So you have to move it. So it must have a spill in there. And the spill just splits, actually split, not a spill. Splits and, go to town and register allocator from there. But that turns into how do you do register allocator? And the SSA is just convenient because you need the def use edges anyhow to go build your liveness.
Right.
So leave it in SSA form. And then register allocator does what he does, and he understands shit like I got ports or I don't, or I have this registers or that, or I need pairs and align pairs or blah, 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 whatever. He all sorts that out. And that's not really SSA. That's just write a register allocator. And And then Alan, one of your comments earlier was like, I want to have optimal code out of my register allocator. And that's like, oh, that's like NP complete at best. You're not getting optimal without being exponential.
Like there's literally a project that does that. Like it's research that's been done, and they've done it. So,
they're whipping out a SAT solver, and performance of it is suck because it's a SAT solver.
No.
It can do perfect allocations, but it's a SAT solver.
It's a constraint solver. It doesn't
SAT solver. These problems are
like more complicated constraints.
Fine.
Like it's like this block packing problem.
Yeah, right. I'm claiming that these things are at best NP complete. Like there's no way you're doing less than exponential in the worst case. Right.
Well, the key is good heuristics. If you have a good heuristic, you can eliminate like 90% of the cases to explore, and then you're golden because you just have
every register allocator engineer everywhere. The key is good heuristics, and it's true. And in fact, you can do quite well, and you don't need a SAT solver, but maybe you want one. I don't know.
It's like the last 10% of performance that you get with the SAT solving that you don't get with just.
I bet you it's not that much.
This sounds like a problem for machine learning optimization.
You have a SAT solver. It's called the runtime.
Dun, dun, dun. No, that's not it.
No,
because
but you do.
This is how you in theory, what's the optimal code generation strategy here, and mixed in with that is like instruction scheduling, because you can lower your register count needs, and you can.
But first of all,
latency.
If it's not a hotspot, it doesn't matter how you register allocate.
I'm sorry, I don't understand that question.
If it's not inside the big O, you could allocate it ridiculously poorly, and it would make zero measurable difference.
It's not inside the big O.
If it's not inside the hot loop. Like what code gets run 400 trillion times? That's the only thing that matters for register allocation.
Right. And what actually really happens though is that you get a big muddled mess of mediocre code. That, at least in the land of Java, you got a big muddled mess of mediocre code. All the hot loops do all the right things and get the right answers. The big muddled code still takes the other half of the time. And the big muddled code now gets well into the, NP complete heuristic game.
Right. But at that point, you actually have runtime statistics to tell you which choices are better. Now you have an SAT solver. It may take years to solve, but you have an actual SAT solver running on someone else's hardware. Gen code one way, measure it. Gen it another way, measure it.
Geez.
Seriously.
That's not going to give you the optimal. Not in any reasonable time in the universe.
No, but you're only measuring it at the macro level. So you may be tweaking minor choices, but you're measuring it at a 10,000 foot height.
But maybe we're talking about something slightly different. This is like, as I understand it, Alan's going to get perfect, but perfect has a definition, which means least counts, loads, and stores. But you actually, as you're pointing out, we need least count execution time, loads, and stores, which goes to profile counters or future behavior.
A load from a cache line is not a load; it's a zero, right? So everything not hitting memory is zero. Well, close.
No, but okay, it's one or three depending on how you want to count.
Right. So register is 0 and cache line is 3. Okay. Yeah. And missing a cache line is
300. Yeah. Right. Yeah. So if
on the 200, 300. Yeah. I mean, like
diminishing returns on the register allocator.
Yeah.
Yeah.
So perfect on the register allocator is running faster than any other possible register allocation. And you won't know that until runtime.
Okay, and then I'd claim the next piece of that one is if I can get rid of a cache miss because I restructure how the data lays out, that so beats anything I could do in the register allocator.
Someone has done something like that for LLVM. The project is called Unison, and they use combinatorial optimizer, combining the optimization problem of register allocation and instruction scheduling. They do notice they have the speed up from 1% to 10% over LLVM. However, you face the limit that it scales up to 1,000 instructions. So it depends on how large your basic blocks are, whether you can use it or not.
Yeah, yeah, yeah. Oh, my very first patent when I was, pre-Java days was driven by somebody taking this stupid Fortran benchmark FFPPPPP and it's unrolled hugely. And it had like one basic block had a maximum live count of like 300 values simultaneously live, and an average live count of like 100 something live, and it was like 10,000 instructions long, and many register allocators just died the gruesome death on that block because it just didn't know how to handle it. And I did a clever hack where I rescheduled while allocating to cause fewer total spills by a fair amount. Actually, we got benchmark award-winning numbers out of that stupid hack on this one benchmark. But yeah, you had giant basic block with giant count of simultaneous live, and register allocation by and in of itself is not the right way to go. Like perfect was not good compared to, oh, we order instructions and then do perfect register allocation. That was a lot better, a 2x. Anything to do with skipping memory because you're smart about your object layout or you're caching things longer or whatever also.
Yeah, in general, I would expect you would get the most leverage from optimizing the spills and the reloads. If you ignore just everything else and try to attack minimization of spills and reloads, you'd probably get most of the performance you would get.
That's where that one benchmark was at. All the time was fix your spill and reloads. Yeah, perfect allocation up to a point, and then it didn't allocate. Now you have to spill, and then like okay.
Well, no, so like the reason it's called unison is because they literally do like 3 different things at the same time. They do register allocation, instruction selection, instruction scheduling, and I think even people optimization. And so like it's all a single code pass.
Okay.
And it's all done. I mean, it's like conceptually it's 4 different things, but they integrate the constraints, and so they solve the whole constraint thing as a single unit. Constraint.
Yeah, so looking at code for power chips, like there's only one instruction you're going to select at any given point because of any risk. So that one wasn't terribly exciting. I've done my peepholes already, but instruction scheduling and then register allocation at the same time had a lot of flex, and you could get some numbers out of that.
They are still working on instruction selection integrated in this framework as a future research. That being said, the dissertation of the co-author, it's called a universal instruction selection. It should be the first result of your rules. I think it's the best resource you have on the modern instruction selection techniques to date, because he actually goes and reviews the existing and recent research of instruction selection. So it's a very good read. Highly recommend it if you're into that.
Okay. I mean, Hotspot did back in the day a fancy schmancy Burrs rewriting engine to go do best instruction selection, and it wasn't worth it. And for 20 years, things got risky enough, including x86, I'd just do greedy and that would be good enough. And maybe things are changing now. I don't know.
Yeah, but if you saw Matt's comment, he posted it in the Zoom chat, but he basically said, so the Unison paper, they only got a 4% speed up over LLVM with all these complicated techniques. So like, I mean, I overstated a bit when I said 20%.
No, 4% was the code size. The speed was actually up to 10%. But again, the main limitation is the basic block size. That it only scales up to 1,000 instructions because it's just to solve.
Well, and it's one block at a time?
I think so.
What do you do at borders where you're merging shit?
I mean, they have a section somewhere in one of their papers about scalability, and like they're saying they could do 1,000 instructions, and like basically, nobody before them could do like more than like 100 instructions. So
10.
I mean, and I think you can do more than 1,000 instructions. You just lose optimality. You have to make, you have to break off the search somewhere because it's just too large.
And well, I was asking a different question. What about control flow, basically? Like the average block length in a Java program is 5 instructions. if you skip the loads being used as null pointer checks, it grows to like 7 or 8 instructions. It's like really short, and control flow is fucking everywhere. And so I need to have a strategy that spans complicated control flow.
We should invite one of the authors as guests.
Do you know any of them?
We'll have to see.
I mean, I'm all good for inviting outside speakers here.
Like part of the instruction scheduling is handling, it's global basically. It handles like branches and stuff as well as
and register allocation.
Yeah.
Okay.
Yeah. So like, I mean, I have to reread the papers again because I've forgotten them already. But it is global. Like in theory, you could do the whole program. It's just that it's too slow. So they found this nice, chunk size.
They got something down to where it's reasonable, whatever reasonable is for an academic versus
I think it handles an LLVM method essentially, like a single function is what it handles, and so that can have several basic blocks.
At least the 2019 paper, the latest one, explicitly says that the scope of instruction scheduling is local, which means one basic block at a time. I cannot find what they do exactly for the register allocation, whether they enlarge the scope or not, because they do have to deal with leave-ins and live-outs between the basic blocks anyway.
Yeah, so I was wondering about the register allocation part. Local scheduling is generally really reasonably done with like a list scheduler. If you've already moved things for frequency in a block that's sensible, list schedulers do fine unless you get this overload situation I was talking about where I want to integrate list scheduling and allocation, which C2 did not do. That was prior to C2. That was very, very early for me.
Okay.
Yeah.
Next.
I think there was some question of where LLVM was fast or slow compared to C2 or Y, and I think we wandered off.
Actually, global. Actually, they claim they do the combinatorial register allocation at the global scope. And they mentioned that several different papers. So it's actually kind of impressive that they are able to scale to 1,000 instructions. They even have a table when they compare the other papers, and the only other global approach scales to 30 instructions. So it's actually a pretty big deal that they were able to go to 1,000.
Yeah, let's say I was thinking the last time I saw these things, it was like, well, GCC super optimizer, which hardly counts, but 10 was its limit. Okay, here they have loops and control flow. I don't think they have any. So you want to put profiling data in to help you with understanding, because that goes to exactly where you want to do spilling. And there they are, doing live ranges sensibly, talking about. Okay, integrated comes from. Okay, fine. I'll have to read it another time. Okay, fine. Yeah.
Yes, section 5 talks about global register allocation. So that's the one where they extend this approach to the global scope.
Right. I'd have to stare at there's local allocation, and they're doing scheduling in here as well. All right, I got it.
Section 6.
Shouldn't be doing, here's split, spill, coalescing. C2 does a split, never a spill. And then the splits can be spilled by allocating them to a stack register where you have an infinite number of stack registers. But coalescing and all that. But these are all done by, and C2 is all done by heuristics. This guy's going to claim, and there's rematerialization. This is all like good old fashioned register allocation shit. Here's global allocation. Probably just they deal with control flow and instruction scheduling. Wow. And here's the combination. Okay, I'll have to go stare at it.
I think this has changed because I remember this being presented on the LLVM developers meeting. It was like 2016, and I don't think it was this advanced back then. So it seems that they continued working on this.
This was what was this paper? When was this paper? This paper is 2019. It's fairly recent. Sure. All right. And then, you know, fun stuff after. Oh, it's like, geez, they got 100 references in there. And here are global parameters. So these are your descriptions of how to describe. Yeah, okay, these are like reasonable. Fine. Yeah, cool.
Yeah, but like you need a constraint solver to make it work. And so like, you know,
Well,
so like I've been saying,
yeah,
I have to implement a constraint solver. So yes,
all
I
right.
definitely.
I'm still in the zone of heuristics get you pretty far for a lot cheaper, but fine.
Yeah. So.
One of the authors actually wants an oracle on OpenJDK.
Oh, well, we should.
So that's interesting.
We should. What's his name?
Roberto. The first author, I think. Yeah, he's the first author.
First author. Roberto Lozano. Is there contact information on the slide? I mean, on the thing here. I have like written addresses, but not an email. Oh, here we go.
He's on Twitter.
Roberto.castiano@ra.se.
He's on Twitter also.
Okay. We decided the Twitter universe is not imploding anytime soon. All right.
No comment.
No comment. Fair enough. Fair enough. Okay. Yeah. I'll reach out and see if he wants to join us for a session and talk about his paper. He's got a video. There you go. And he's doing it for a DSP that makes total sense, which is, say, you have small programs often that need careful, close to perfect. You're willing to take a long, slow time to do it. Rectangle packing. Register allocation is rectangle packing. That has been a long time since I saw a real register allocation paper. That is very interesting. Yeah, fine.
Okay, changing the topics maybe.
Yeah, what else? Let's see here. Aaron's still on. Just for your benefit, I'm still hacking AA. Now I'm moving into the main code base and doing Henley Milner on the main code base. That was the new thing and the new way to do primitive execution. And Christmas. So that was my last 2 weeks. Been busy. Had 10 people in the house.
Does that mean you get a REPL?
I'm sorry, say again.
Once that's in main AA, are you getting close to writing the REPL?
Oh, yeah, the REPL's waiting for the thing to parse. Yeah. So no, I'm on, you know, what test parse 00, which has like 50 tests inside of it, and I'm on test 45 or something. So out of my 1,000 tests, I've done, you know, 1% or something, 0.5%. No, 5%. So a lot of the tests are somewhat redundant. I'm assuming it goes faster as I get further along. And then I'll hit the point where I ran into, I absolutely had to have Henley Milner, and then it'll get exciting. So, you know, this last week when working it, I knew Henley Milner and main AA, not the research version, and new way to execute primitives. They do the overloads and get the overload code ported over as well. And then I ran into errors in the flow analysis, similarly errors in the, real errors. You wrote broken code, and the compiler is supposed to give you a type error and reject it. And I get a different error out of the Henley Milner, and now I want to report a uniform error type. So I'm having to make the errors be uniform between things. And I'm not even out of the first go round of test things. But I think a lot of the stuff that comes after this is going to be, you know, already worked out. Like the parts are all squared and straightforward, and I'm missing like shit like function calls because of typing with Henley Milner versus flow typing is a little different. So I have to screw that around, and that's work in progress and getting close. And then I think I'll make big steps forward in the test cases When I get down to where the test cases have sort of like all stabilized and I'll break out future work like for arrays, I'm just going to postpone them for a little bit. I'll probably go make a REPL.
So from your perspective, which one is more interesting, the JIT compilers or the type theory stuff?
Oh, well, I'm afraid I think I've done new work in type theory and I'm not hugely excited. I just needed to have it done. So I want to get something, I'm with Aaron, I want to get something I can write code in. You know, write code in Anger, even just tiny little test cases that you can see that this is doing something sensible or not. You can't, like we do a lot of, you know, I won't say mental, funny, insert your favorite bad word here, but mental gyrations to like guess what AA code would feel like. And it only goes so far. And you actually have to, you know, write some code and see it work. So I want to get to the bottom of my standard. This is how I do test typing things. And I'll postpone arrays because I don't think they'll have anything excitingly new in either implementation or on type theory side. And then I'll go down to beat on the REPL and get me a, you know, something that just executes CF nodes directly as an interpreter, as a poor man's bad interpreter. And that will move the state of the art a lot forward, I think.
Move things along.
Yeah. Because like I said, you only go so far if you can't actually run anything. So we're just playing guessing games. Hey, this looks pretty cool. Oh, that looks pretty cool. Oh, that looks fine. Not, whatever. No, fine.
Yeah. But your experience has shape on the language. You know, you have looked at language X years.
I'm making a guess.
You know what it should feel like. That's a problem.
Right. That's my guess. Cameron and I both had this comment some time ago in the Discord. It's like, you know, in the past, I thought I was doing cool shit. And then now I look back at some stuff I've done in the past. I'm like, you know, some things were good and some things were definitely not good. And I'm like, well, I fooled myself then. Am I fooling myself now? Oh, don't know yet.
Of course. It has to be fun.
I think everyone who learned Lisp went through that. Oh, look at all these macros I can use to make it nicer. Oh, wait, that was not a good idea.
Right. Well, I use C++ templates. Oh, I went an operator overloading. I exploded all over C++ operator overloading. And then, you know, a year or two, well, 3 or 4 years later, looking back on it, oh, God, oh, stop, you know. And template expansion. And well, we did a hotspot with C++, and of course they had templates, but the team quickly realized that they were is a quick way to shoot yourself in the foot. So long before the standard template library was ever around, we had vetoed all templates except square bracket arrays for resizable arrays, you know, internally doubling arrays, Java array lists, basically. But all other overloads and operators were declared verboten, thou shalt not. I think
it isn't in the programmer's nature to go for the most powerful thing in the language.
Right. The language hands you lots of cool shit and you want to play with it. And then when you come back around to like reading it and understanding it and dealing with it the next year, you suddenly realize that this is all actually fairly opaque. I mean, you know, there are places for a DSL and there are places not for DSL. And C2 kind of had a place for a DSL, but much of the runtime in Hotspot did not need a DSL, and operators just went crazy there. So we backed that way off very early, so that just was a no. The square bracket thing for array lists, terribly convenient, so we kept that one. Everything else we went with classic macros and just stylized coding.
I think templates don't help that much if you just use them for generic programming, by which I mean containers of type T and the algorithms that operate on collection of elements of type T. When it may begin to hurt is when you start using this specifically for template meta programming, when you use the fact that they are Turing complete and you're trying to evaluate arbitrarily complicated expression. But in LLVM experience, that doesn't seem to be a problem. People don't go into heavy TMP, and generally the templates that are used in LLVM containers are very useful.
So
I think you can solve that problem in practice.
let me translate that. So LSD, it can be used as a sleep aid, but we don't suggest it.
No comment. No, but seriously, I think you would suffer more from a programming language that doesn't allow you to make a container of arbitrary type, and you would have to copy paste every single container rather than a language that has too complicated templates. If that's the trade-off, I would still go with C++ rather than pre-generics Go.
I certainly, in the land of C, you know, we did generics, void star generics, right? That was a common thing. And that meant as long as your containers were either, the array thing.
It's good to have type checking still, I would say.
No question. And, it wasn't available, so we rolled with what we had. And the containers for the square bracket array doubling thing, the syntax is nicer than array list .get and put, in my opinion. And we did have things that were shorter and larger primitives, but as soon as you went to pointers, it was just void star polymorphism. Usually you then wrapped it in a whole class of accessors that do the casting under the hood. So you knew that your container, you talked about not the generic array list container, but about the foo container, the method container, the whatever container, and he had method casting going in and out, and that, made it like, that gave you a feel of having typing back and contained the unsafeness.
But I think a lot of the bad experience with templates in C++ comes from the 1990s, when the compilers didn't really implement templates very well, or implement them very inconsistently.
Very inconsistently, and we were trying to be write once, run anywhere, so we had to be portable. So we were running compilers on all platforms. So it was a large scale C++ on purpose mini targets build. Solaris and Linux and Windows and Mac as a minimum, and the IBM OS2 and everyone's compilers were at a different stage in their their template handling.
C++ that Bjorn initially set out to prove that he could do generics like the other languages. And somewhere along the way, people are like, this is way too complicated for generics, but look at this really cool thing I did with it. I kind of rewrote my program with my generics, and then he's like, oh yeah, that's the feature.
Just to show off, that was
just to pretend he was right all along.
In order to demonstrate your mastery in a language, you have to demonstrate its most complex features.
Yeah, absolutely.
In a opaque and obscure way.
I totally get that.
That's fine.
I am not attempting to go there in AA mostly.
I'm just worried if I'm broken, because I don't even consider templates to be among 10 most complicated features of C++. So maybe it's Stockholm syndrome, but I wouldn't put them in top 10.
Oh God.
Honestly, usual arithmetic conversions to me are far more tricky than templates. Everything that has to do with integer promotion and implicit conversions, I would put that as difficult, not templates.
If I compare it to the Scala generics, I would say
I was going to say copy constructor versus move constructor versus update in place or whatever things. I think that was, in my head, that was the most subtly, stupidly broken portion. Operator new and operator delete and all those friends. No? Okay, fine. All right, are we done wailing away on C++ yet?
I used all those operators.
Yeah.
That's how you do arena allocation.
Yes, I exactly used them for arena allocation. Yeah. And I had rapid deallocate that would unwind the arena pointer as part of the complexity there. It was, I don't know, kind of an obnoxious thing. I don't know how you make that kind of shit type safe. Here's a raw chunk of memory that's not truly
Right.
free OS memory, it's arena, and then I'm going to declare it.
But C++ and C kind of share the same non-type system.
Yeah,
Right.
fine.
You're allowed to put bows on things, like you do Christmas presents. You're like, okay, this is an int, trust me. This is a pointer to a char, trust me. This is a
Yeah.
const something, trust me. So it's the trust me type system.
Yeah. Fine.
Hmm.
Well, it works pretty well. You can get a lot of
Trust
shit
me.
done in it.
Trust me.
Trust me, it works well.
Works well, trust me.
Note
We're all
that
running
this
tools built on
comment
this shit.
applies to most languages with reference semantics, particularly if your language has nullable types.
No, it's good.
Trust me, it's not null.
Trust me. Absolutely. Oh, holy moly. All right, fine. What else? No?
I finished the first pass on the automatic sizing integer stuff. So got the APIs done on the idea being you have a integer that the runtime can choose how big it is on your behalf based on profile data. So we
And
had
you keep growing it if somebody keeps making the number bigger so that it doesn't, it's a bit,
Here-
semantically, it's a big integer.
yeah, we haven't gotten to that point. It's int 128 at max.
Okay, but semantically, it's a bit 128.
Right, but it's a weakened semantics so that we can, so it loses some of the operations from the int class. So, so we constrain some of the operations related to bit.
Like
bit
rotate.
Right, there's no rotate.
Okay.
Cameron, in Ecstasy, do your floats default to binary floats or decimal floats?
We have both, but we're going to push people for most applications to use decimal, even though it's fuck ton slower. Just because binary floats shouldn't exist outside of machine learning,
Why not?
because they don't exist in the universe.
Well, neither do decimal floats.
I have 10 fingers. Decimal floats exist. If you teach cows or pigs to count, we'll have binary floating point.
Okay.
Hey, I got a smile out of yours.
I got two hands, so I got two middle index fingers.
So yeah,
Sorry.
binary floating point numbers were a reasonable beta.
They were hugely better and have worked hugely well for 40 years. The hugely better what came before and worked hugely well for 40 years.
Yeah, I mean, when we first hit 10 kilohertz for a CPU, that was the time to start moving away from floating point numbers. But I'm sorry, binary floating point numbers. But so we have three types that are automatically sized. We have an automatically sized int, a 127-bit automatically sized uint. Yeah, I'll explain that in a second. And another auto-sized decimal, which is again up to 128. And the reason for the 127-bit on the uint, because remember, we have uint 128, we have uint 64, and so on, right? The reason for 127 is because it allows you to use the uint as kind of a constrained int, a magnitude-only int. So because it's only 127 bits, you can pass it as an int. So in other words, when do you have to specify a conversion? We only automatically convert types under two conditions. One, it's explicitly, that the type itself explicitly declares it automatically converts. And two, that we don't lose data.
Right.
So,
and I say there's no ambiguity about choices of what you're converting to and from.
no, that's all based on bidirectional type inference. So if I'm calling a method and the method takes an int and I'm uint 8, then it'll automatically convert from the uint 8 to the int because uint 8 has an auto convert to, I mean, it's a method on uint 8 called toInt.
Okay.
So if uint were 128 bits max, then we couldn't have an auto convert to int.
But the benefits wouldn't be the uint that we use the host 128 bits. So
Right,
if you,
but that's why we have uint 128. If you know the size you need, you just use it. If you don't know the size you need and you want the runtime to choose it for you, then you specify int or
When you
uint.
say I
kind
don't know
of
what
view
size I
size.
need, I'm asking, what are the semantics? It behaves as if it is an integer up to 128 bits. I'm asking.
Yes.
It
Yes,
doesn't
so
roll over to
int-
big integer.
Int does not roll over to big integer.
Okay.
It goes all the way, it's always checked. So if you overflow from 128-bit 2's complement int type,
Yeah.
it's an exception.
Okay.
It's kind of CU size.
But you throw the overflow check on every math on it.
Well, I mean, it's a liftable operation, but yeah, generally speaking, you have to, in theory, you have to check every operation.
Yeah. Okay. Yeah. Yeah.
I
Same
mean-
as Java range checks or
Right.
null pointer checks or
The
whatever.
idea is that int and uint, well, mostly int is kind of the type that's used everywhere in the language. So a for loop, you know, you say for, you know, it's usually an int. An index into an array is an int, right?
Yeah.
So how big can an array be in Java? Well, 2 billion elements divided by size of element, as discussed last week or whenever.
Yeah. Sometimes 2 billion and sometimes divided by count of elements. Depends on the VM.
So in this case, you know, it's mainly going to be beneficial for properties on classes that have many instances. Because going back to the register allocation discussion, right? Who cares about a class you have one instance of, right? No matter how small you make the fields, like, okay, I shrank it from 64 bytes to 16. Congratulations, you save 48 bytes, you
Yeah.
know, and you've got, you know, 30 terabytes on the server. On the other hand, if you have 30 trillion of these objects, like big data,
Yeah.
you know, your records there, you know, being able to shave bits per all of a sudden becomes huge. And in fact, we also added a couple months ago, we also added the M5E2, sorry, M2E5 and M3E4 floating points as well. So those are 8-bit floating points.
Mm.
And we already have support for, well, what support? I'm putting this in quotes because this is not all important, but for bfloat 16. And again, the reason is because when you're doing machine learning, it's like, you don't want the computer to learn that it should have used a smaller floating point, right? So there's no way I can do an automatic binary floating point sizing. I can do decimal because the numbers are actually exact, right? Like, you know, $1.10, right? I'm talking business applications for that, but for machine learning, I basically need to know, is it as big as a mountain, as big as a bread box, or as big as a watch, right? Like, or as big as a molecule, right? There, like, all mountains are the same, all watches are the same, all bread boxes are the same. You know, I can squeeze that down into 8 bits and double the number of data points in the model. So I lose a tiny bit of precision because I give up on the mantissa. But
Well,
I gain.
I think
I
you
gain
asked the
stagger.
user what he thinks his data range is. I've certainly had data sets where I only had 3 bits of precision in the data I gathered, but
Right.
some places I had, you know, 10 and 20 bits of precision in the data I gathered, and I wanted to keep that.
But
So
that's why
asked the question.
that's why you'd have to specify the size for those. That's
Yeah.
not an automatic.
Right. Right.
But you know, I think decimal is a very good default for most business applications, and the lack of decimal has been a huge disaster for many years.
Binary was right for Fortran, and decimal was right for COBOL.
Yeah.
That's actually a fairly reasonable way to put it. I think.
Yeah, and I think most of our applications look more like the COBOL use case, but our languages look more like the Fortran language.
I think that is also a fairly good statement. Yeah. Although, you know, I'd rather not be associated in any possible way with either of those, just for the record.
Well, as soon as you say decimal, that COBOL just comes right there. Comes hand in hand.
Yeah. Well, I mean, decimal in the sense of character data holding numbers. Yes, I recall.
Yep.
I mean, they claim to be a business language.
Yep. Well,
fairly-
I assume Ecstasy,
fairly
Ecstasy
common as
also
well.
claims to be a business logic language, right?
I would like business applications to be able to be built in Ecstasy. Yes. And I mean, obviously, a lot of the security features, the avoiding the thread, you know, the shared mutable stuff. I mean, all that points at, you know, I'm not trying to sell this to Cliff.
we already had that discussion.
Exactly. Anyhow, or Alan. I'm not trying to sell it to Alan.
Yeah, so that was new for me from Alan. I hadn't seen your take on performance and bare metal before.
Cool.
Yeah,
So anyway.
yeah, fine.
So that's what I've been doing.
All
Aside
right.
from, but good to get it done.
I mean, if we're done here, I have like another topic I wanted to pick up on, because like we were chatting about way too much stuff in the Discord. Like I was like, why didn't we have a CCC meeting already? I want to talk about this instead of, you know, with my voice instead of writing all of it down. But anyways, so you wrote that, like, what was it? It was like 90% of methods have to be statically dispatched for good performance.
Get to be statically dispatched, yeah, or more, yeah, right.
So I was just wondering where that number came from.
Came from measuring the hotspot.
Okay.
On, you know, big business apps, so whatever you call a business app, so JBoss, WebSphere at that time. And you go through the math, and like, unless someone said final, it's a virtual call in theory. And then, you know, statically, C2 takes 90% of virtual calls, and CHA cleans them out. Class hierarchy analysis cleans them out and turns them into a static call. Now that it's static, it maybe gets inlined and there's no call ever or whatever, fine. Of the 10% that didn't get made static, hey, see you, York, that are dynamic, you throw an inline cache down, and inline caches work like, you know, 95% of the time. The compiler couldn't prove it, but inline cache sees there's only ever one target at runtime. And then of the remaining, you know, 5% of the 10%, those go megamorphic on you, and you take a load jump register. And that was, you know, sort of well measured and well understood, and been true for a long time. And I assume the ratio changed a little bit, and people who generate code for like Groovy and Ruby and Python on the JVM totally fall through the cracks and hit the bad case all the time. But if you're like writing Java code to do shitty Java apps on a big, you know, big Java server, those are the kind of numbers you get.
Okay. So this is like the invoke virtual bytecode call is what you're in.
Yeah, invoke virtual. That's right. You see an invoke virtual bytecode, 90% of them, you do a little class hierarchy analysis, and you got it static, and you're done.
All right. Okay.
Yep.
I mean, there's not much to say. It's you just
no. It's fair. You know, why does that apply? Right? Am I going to write code that's going to look like this shit? I don't know.
Yeah,
right?
We're going to aim for about 99.9% of non-virtual, because short of that, we're going to suck.
As long as your count is, well, I mean, I was 5% of 10%, so I'm 0.5% or something. And you know, that's low enough that you can be 30 clocks and not notice it.
Well, because everything in Ecstasy is a virtual.
Right.
So,
but
yes,
your theory is
of the virtual.
Yeah, your theory is it's going to actually clean out, which is what happened to Java. 90% of or 99% of all calls are virtual, and nearly all of them clean out. So, and the heuristics for inlining and the shit like that got better over the years. So in the beginning, people sometimes sweated and sometimes got the wrong slow method call, and sometimes demanded final or thought they had to final, and that kind of faded after 5 or 10 years, and use final
There's a
now because
whole
it makes sense.
overriding methods inside of subclasses is rare.
It's not that it's rare, it's that
Classes are rare.
the JIT getting it wrong is rare. That's what I'm just saying. Just if you didn't override it, in fact, yeah, it's rare. And then you're even a base class, or a final class of, not a final class, sorry, you're the leaf of the class hierarchy. nothing you wrote in there needs to have the word final. I know that the class has no subclasses. All methods are exactly what they are. There's no virtual dispatch required. Yeah. The coding styles kind of also maybe migrated to where fewer overloads, but if you had a bunch of overloads, you probably went megamorphic, and that was your intention. And then the dispatch is exactly a reasonable dispatch for a megamorphic call. You did a couple loads in a jump register, and there's not a whole lot you're going to do better about that.
Well, I mean, you could do the inline cache stuff if it.
That's what I'm saying. Once you're past inline caching, inline caching is great, and like I said, it covers 95% of the 10%. But if you're doing a whole lot of calls to a whole lot of targets, you're kind of stuck with load, jump register. You can do 2 loads in a jump register with a little more screwing around. If you have a highly weighted distribution, so there's one really popular target, and you get that with profiling, you can do better. You test the one target in inline.
But typically inside the for loops, you have only one instance of the class.
Yeah, and then there was an optimization put in C2 specifically for direct byte buffer and heat byte buffer that exactly handles this. You had some virtual calls. They were all to the same virtual class, which was totally one of the nodes in a sea of nodes IR. I loaded the class, so I knew it was a guy, and it was loop invariant. And then it made calls off of him being loop invariant. Okay, I want to make 2 copies of the loop. And do the left or the right. Oh, yeah, the guy that I pulled out had 2 hot children underneath him. Well, I make 2 copies of the loop. One for the one for the other. Be done. That was a long time coming, pain in the neck. In H2O, I did that by hand, and then I called Java Assist to generate bytecodes where I broke out the classes, because the JIT wasn't going to do that many different targets.
So I don't know. Is there a magic bullet that would make it easier?
I don't know. It'd be nice if the JIT did all the targets, but you have a real balance to walk between code blowout. The Julia experience taught me that unless you do some smarts, you get code blowout. They had iCache suffering. They were 10 minutes to boot. That was all generating all the different replica versions, because statically they existed and could be called. Dynamically, you could have postponed the blowout by having only statically compiling target methods for these particular specialized, but you got to do some careful trimming, or you iCache blow out yourself.
Okay, so you need like a very detailed model of how the processor's caches work, and then you have
not a detailed model of how the caches work, just a understanding that it's finite sized.
Okay, well, you need to know their size.
Yeah. Here's a 64K. Is a 32 or 64K is like the dominant current size set for this. Okay, fine. So I come up, I want to specialize some code. Well, the hot inner loop after I unrolled it was already 2K long, 3K long, and I got one version for ints and one for unsigned, one for bytes, and one for references, and da. And if I'm calling them all interleaved, then I got 8 variants at 2K a pop. I'm burning 16 out of my 64K. It's a substantial chunk. And Julia came along and said, well, I'm going to specialize for every possible variant. So I didn't have 5. I had each of the different arguments at each of the different variants. And so I got this quadratic or cubic growth. And so there were hundreds of variants for the same method. And if you got some hot loop over things and the inner loop was kilobyte and you had hundreds of variants, you blew out your iCache. And you burned all this time generating all these methods, and it didn't help because you blew out your iCache.
Okay, that actually made me think of something. So the 64K number, right? So if I can get a register allocation to work on a sequence of code that size, right? Then it probably is optimal, because anything larger than that will blow out the iCache, and so it'll swamp whatever benefits register.
It's not a method boundary. The method has to get walked through up to the hot code and then walked out of. So in C2 land, there's a path that's considered, well taken. Profile says you've been here a lot. There's a lot of offshoots. The offshoots go, low frequency or cut off to the interpreter because they're so low. They generate a lot of code because I don't spend a lot of time optimizing on them either. So the spiller, takes shortcuts there and they kind of get puffy, and you throw them at the end and they're rarely taken. So it's not that you want to do the whole method, you want to do the hot path through the method. And then you want to have a bunch of these methods in the iCache at the same time. You're not having only the one.
Right. Well, I mean, like, okay, so like I implement something where it decides, oh, this is too cold, I'm not going to pay attention to how it's allocated. Right?
Yeah, you have to be correct but cheap.
Right. And then like, so I have a cutoff, and then like the exploration space, that the tree it's exploring, like it just has to cover 64K of instructions, and then like
no, I'm trying to say you get a lot of stuff that's kind of mediocre that you want to do well on, and it's never going to hit 64K individually, but you have a lot of unrelated methods that are all co-calling each other that you haven't inline to the nth degree, either because you can't or because, again, iCache blowout and you've carefully arranged it. So just saying a method.
Well, yeah, no. Like I'm talking about like, like, I mean, if I identify some amorphous, hot loop.
Okay. Yeah, right.
Instructions.
Yeah.
And so that that's a good chunk to work with. And like, if I register allocate that, then like I'm good.
Yeah, I mean, it's a little naive because these things roll along. Like I have a ball of hot, and I have a little bit over here for a while and a little bit over here, and this goes away and a little bit over here, and the ball stays, and then you do a big phase shift and you load a whole new ball in for the phase shift change, and then you do another similar situation. It's kind of more how I think about it as. You definitely, like, the iCache blowout thing is a big deal, and that shows up in how you do inlining way more. So if you have a lot of mediocre methods calling mediocre methods, which is totally the thing that happens, you don't want to have a medium-sized mediocre method inlined in its caller too many times. You get a whole lot of versions of a medium hot guy from different contexts, unless the context just guts him. You lose. So you stop and say, this medium guy of medium size, I'm not going to inline him anymore. I could, a static call, I know how to do it. He's too big. I'm not going to inline him. And you have to make those decisions as you're going through your inlining and jitting. And that's like more important than register allocation by a fair amount.
Well, okay. But like, I mean, I'm pretty sure that like every decent program is going to have like a main loop in it. Like it's going to read network requests and respond to them, or it's going to, I mean,
then you may not spend hardly any time in that main loop. It could be all your time or none of it. It could be I'm doing Mandelbrot's in a loop. It could be I'm doing network requests and all my time's in a sea of code doing web parsing and database lookup, and I come back to the main network handling.
Yeah, no. I'm thinking of the loop as like including every method it's called. So like,
yeah,
I like it. It's always on the stack somewhere.
Yeah, it's high on the stack, but you're never getting back to it, as I'm saying. It's commonly the case you don't get back to the top loop. You go down and you fiddle around at the leaves for a long time, and then rarely go back to the top and get a new piece of work, and then you come back down. In that kind of a scenario, I kind of don't care what the top's looking like. I care that the leaves in the middle and the bottom are all that bushy behavior. Those are all well done.
But if I can like start from the main loop and like I say the main loop calls all these methods and I know which ones are hot, and like I like suck up 64K of hot instructions from the main loop, and then everything else is like a new 64K chunk, and then I optimize those.
I think you should go implement and have a large use case of many users, so you get a representative sample that's not something that you and I are making up on the spot.
Well, like, I mean, I can't do
Yeah,
that's what I'm saying.
That's actually the well-known case is the memcpy function and vectorization trading off with the iCache. Because if you consider the memcpy function, you probably have seen the implementation, which for SSE or AVX dispatches to different sizes of data, right?
Yeah.
And it may be that for data size that has, say, 500 bytes, 1 kilobyte, 2 kilobytes, and 16 kilobytes or more, different vectorized version is better. And if you specialize your memcpy and write it for every single version, you are going to have fantastic performance on micro benchmarks. And then when you deploy this in the application used by the end user, you are going to tank performance of that application. And the reason is that, say, memcpy for SSL3 in glibc already has weights like 10 kilobytes of size. And remember, your iCache has 64 kilobytes. So your memcpy is taking 1/6 of the entire instruction cache just because you added all of those smart optimizations that performed well on the micro benchmarks. So just be careful with that, because you may get exact opposite performance. Something that wins you every single micro benchmark is going to tank every single user application.
Here the types would benefit. If you know the types, you can specialize early. So the type is
that's what he's saying is you don't want to
No,
specialize at all, is because whatever you specialize, it'll take up more instructions.
Or only specialize at runtime. Specifically in the JIT compiler, you would have to synthesize specific memcpy version for specific workload, and make sure you don't lose too much on the mis-speculation in this optimization if the version changes.
So like in the land of, you know, Java implementations, having done this a couple different times on a bunch of architectures, there's a tiered trade-off. You do a short trip count test in the code, and then you put a dumb byte loop, and then you do a longer jump to a static shared code that does the I'm medium size and I'm large, and some very large size probably jumps to, you know, C routine and does a thing. And you hit the large routine occasionally, and if it blows out your iCache because it's so large, it's only going to get called because the data you're moving is so large that your dcache got completely flushed anyhow. So I think that's okay to have it like that, as long as you don't inline that giant guy. You just have one copy. Now, the different variants, they only go power of 2s on the bytes, so you don't get any byte shearing. You get 1, 2, 4, 8. Sometimes for the ref version, which is either 4 or 8, according to the size of your refs, you also do a hack where you optimize for the GC overheads, like store card marks and the like, read and write barriers, erase store checks. If you're a bad version of a bad thing doing ref things in Java, you can have erase store check loops that are all out of line and handwritten. And then that doesn't blow out your iCache unless you're already going to blow out your dcache anyhow, and you don't care anymore. So you only get a couple versions. You do have to do alignment specialized versions because you can't do shearing of subword pieces. So yeah, 1 byte version or whatever, under 10 bytes. And that one's probably just unrolled directly in the code. And then somewhere between under 100 bytes is a first cut loop. And somewhere under a kilobyte is a second cut loop with prefetching. And then there's a third version somewhere that goes balls to walls. Yeah, I don't do so many. I see you, Matt. I said my experience is once we did what we did, I just said to you, memcpy kind of dropped off the map in terms of cost, except the actual cost you had to do the copy. There's no dodging the loads and stores. Yeah, Cameron says 30%. I totally know. But having said that, the number of instances of memcpy floating in your iCache are probably not very many. You get, like I said, you get a tiny one for short copies that are runtime checked, and then you jump to some shared code. So there's only one copy of it in your iCache for a couple size variants. And then definitely Google sees giant ones where they go balls to walls.
To be clear though, the fact that memcpy exists and is implemented by the CPU is a failure of design. And it mainly exists like that because CPU manufacturers make a lot of money by doing memcpy. So
I know they do it, but I don't think that's the design of the CPU designer.
I mean, the idea is pretty simple, like in a distributed system, and you can think of DRAM as your distributed system. You never want to drag all the data through one node to process it. So the memcpy is basically like the way most idiots write distributed systems. They have one server that does all the work, and it goes to server 1 and gets all the data across the network and processes it. Then it goes to server 2, gets all the data across the network and processes it. It goes to server 3 and gets all the data across the network and process it. It's like dumbest shit you've ever seen. And that's what we do with memcpy. We go to the memory bus, we drag the memory into the CPU 64 bytes at a time for the sole purpose of sending it back out of the CPU. And that's most of the contention on the memory bus right there. It's a huge failure. And it made sense in 1980 when
this has been known for forever and a day, and I claim that it's not a failure in the sense that the solution is somebody who pushes the work down to the memory buses and keeps it off the CPU. It's still going in one DRAM chip and out another, or out one DRAM chip and into another. So it's hitting some set of buses, and at that point,
it goes back to the example you gave of the 2 stores of a cache line when you really need 0. Right, like because of the lack of the 0 on.
Yeah, cache line 0 is a different use case, because I know for a fact that what I'm reading is dead and what I'm writing is dead.
What I'm saying is that, tell me which memcpy implementation does not trash the cache of the CPU.
All the ones that do short copies. There are a lot of short copies. Right. No. These things have this nice inverted, inverse thing. You get a million.
Short copies make perfect. Short copies make perfect sense. I load 4 bytes here, I store 4 bytes there. Perfect, right? But anything, anything that exceeds a cache line should be dumped. And if you look at the old C runtime library, the assembly for it would basically go up to a boundary, then it would switch gears to a different implementation, and then it would get to the last full paragraph boundary, and then it would switch back to kind of a byte at a time mode or something.
That's every memcpy I've ever implemented. Yeah, and I'm still saying the whole thing that the thesis I hear you say is large memcopies should do something that avoids the CPU. The issue here is the CPU is bored, can't do anything while this is going on. And also the memory bus is saturated, and the CPU can saturate the memory bus just as well as a hardcore DRAM on the spot can do it. And DRAM controller on the spot can do it. He can force it from one DRAM chip to another in just the same amount of time as the CPU can. So just let the fucking CPU do it. This is how it got explained to me by the Azul CPU designers. We had this very discussion amongst many, but yes, memcpy. He gave me a cool hack in the CPU to help ease misaligned memcopies. But otherwise, memcopies are like, yeah, what the hell is CPU doing anyhow? So he can run the cache just as fast as anyone else.
The latest DRAM designs actually include processors on the memory chip.
Yeah, if you're going within the chip, there's something you can do there. If you're leaving the chip, you don't want to make that bus to the CPU any slower or more complicated. So the optimal path is to the shared CPU bus, okay, and back. And then now I'm going to go back out to a different chip and on the CPU bus, and the CPUs can just gate those just as well as anyone else. Oh, fine. That was my lecture given from Jack Shaquette.
I believe it. I mean, what I'm suggesting didn't make sense 20 years ago. And
no, this was not 20 though. This 15? Has been true for many years and was true up until a decade ago. It might have changed in the interim, but I haven't seen anything in the latest CPU design, motherboard memory CPU designs that say it's different. Going from network to memory and network to CPU, there's some games there because networks are fucking fast, and you might be able to do something sensible.
Yeah. Well, we worked with Intel to put the CPUs onto the network cards as well for the SRIOV on that we used in the Oracle database. So SRIOV, is that the right?
Yeah. Yeah, I think networks there's room for doing something smart there.
Yeah, but same reason. You didn't want to force an interrupt on the CPU to handle data on the network.
Yeah,
and
you wanted to move the data quick as you could to memory, and if you had to bypass the CPU, you had to have some way to get the CPU off the bus. But Intel designs were doing that.
Right. It's easy to go directly from PCIe to memory on an Intel system because you've got the DMA architecture. So everything riding on the PCIe bus has direct access to, well, direct is a in quotes, but direct access to memory without going through user land. Yep. And with, interestingly, by the way, with NVMe, you not only have direct access to RAM, you have direct access to storage. So chew on that.
I feel like the problem I used to run into there was more that I did a syscall and went into kernel mode and it dumped a bunch of caches just because I switched to the kernel, right?
Yep, yeah, syscalls have gotten way more efficient though. That's one that's gone relatively down dramatically.
The load partial, store partial, Matt, was exactly the extra instructions we got on Azul for moving misaligned, byte-wise misaligning. And we could get the same behavior of full cache line at a time. Fine.
So I'm trying to think though, they're on like, what is it? It's like the 5th number. I forget what the acronym is, but it's like the 5th version of whatever the RAM standard is.
DDR5?
Yeah. So like, I mean, and my impression is they still haven't actually maxed out like the bus bandwidth yet. So like, I mean, so like, maybe DDR7 or something, they're going to, start introducing, clever, communication things that reduce, the bandwidth usage. But I mean, my impression is they aren't there yet. Like nobody's worried about running out of.
For memcpy, you mean?
Yeah, for memcpy. I don't know. I mean, maybe we'll see it, but it's like they're not there yet.
I'm pushing for a better CLZ to handle the standard allocation patterns where I know it's dead coming in and it's highly probabilistically dead going out. Isn't there something we could do to avoid all that bandwidth? Fine. All right. Well, I look forward to your memcpy implementing straight DRAM to DRAM, Cameron.
Oh no, that's not my cup of tea.
No, like I mean, the question as a programming language designer is how do I avoid using memcopies as much as possible? So
why are you using memcpy now?
Well, because you have to. I mean, if you're dealing with immutable data and you want to modify it, then you have to make a copy. So.
Okay, and if I'm not dealing with immutable data, I still make copies. It happens all the time.
No. You just think you're dealing with mutable data. It's all immutable underneath because it's a functional programming. So.
No, I'm talking about an actual x86. It's fucking mutable everywhere. Underneath.
No, you're running in a virtual machine. The virtual machine has a total copy of the state, so it's pure.
All right, fine. But then, as you just said, you got memcopies everywhere.
Yes.
The actual hardware is really good at memcpy, and it gets used a lot for memcpy. That's the takeaway on that one. And is there a better way to do memcpy? Not without changing the silicon fairly heavily? Maybe. All right.
The reality of our programs is we do. Like, if you look at Google's data centers, what is it spending time on? It's spending time on deserializing protobufs, memcopies, and reserializing protobufs.
There's a lot of it going on. Yeah.
Like,
absolutely.
The actual part of Google that does the work is a small part of all the work that gets done.
I suspect Google has a pretty strong notion of what they'd like to do better there, and they have enough money that they've probably thrown it at it. And if there's something to be done, it would have been done already. That's my guess. I mean, of all of the wins and loses and fails and successes of Google's, I claim their engineering is still really good. And there's no reason to believe that they wouldn't have beat on this if they thought that beating on it would have been successful. Fine.
What's that game? Very large organizations like that will often trade off performance of the system for performance of the developers.
Oh, yeah.
Why is this thing designed in such a way that we're spending all this time on serialization? Because that means service A and service B can be relaunched independently, and those two teams don't have to talk to each other. So they are willing to spend a lot more on compute if it reduces the amount they spend on meetings. because
makes
brains are more expensive than CPUs in the average case.
Yeah, that makes more sense. That makes sense. Yeah, that's true of a lot of places and a lot of things. Why aren't we all designing our own chips? Well, Intel's really good at it, and it's really expensive. So Intel does a chip design, and we have to live with the chips we're given. And we can do cool software shit above it. And if you've ever watched Intel thrash about trying to do cool software shit, they're kind of okay in the land of C compilers and linkers. And I haven't seen very many other software products out of Intel that I've been impressed with. Fine. We have our specialties.
All right. So we'll all specialize in our own things and the wealth of nations will increase.
That's been the pattern since the medieval ages. All right. Are we done lamenting history? Is it time to go get lunch? And it's just been rainy here, like depressingly dreary and gloomy for days on end. Fine. I need to hit some sunshine in my life.
That's good coding weather.
It's good. Yeah. Okay. Fair enough. I have been heads down, going to town when I've not been interrupted instantly, continuously by my kids and Lisa's kids and cleaning the house afterwards and whatever. Fine. Many of the kids brought laundry as well, and of course, everyone had sheets and towels.
That's what I was doing on half this call, was catching up on laundry.
So yeah, yes. Lisa did like 7 to 10 loads, like 2 days, 3 days in a row. Oh. Fine. All right. To the wealth of nations. Until we meet again.
Happy New Year. Bye.
Yeah, Happy New Year.
Thank you. Happy New Year.
Happy New Year.
Happy New Year.